show you at one and two. This is the situation. Now, how to stabilize it? That was the yesterday this thing, like where to put the resistor and stuff like that. So I'm coming to the second part of it now. In this case, you have given me with the simulation some time because they are in all different windows. So I will switch off. See. Okay, this is the first type, as you see here. This is the input side. Okay, this is a device. I'll show you the input matching network. Fine. You see here I use a resistive element to stabilize it. This is not correct. Okay, because I have used resistive element at the input side. It's gonna disturb the noise figure. My goal was less than 1 kilo. Okay. I can stabilize it by putting a resistor at the input. This is my device. This is the input of the device. I'm putting it here. I can stabilize it putting a resistor at the input or at the output. Here I have used at the input side. Okay. Now I run the simulator again. Show the nuance figure. Look at the noise figure. Center of the band. It is 2.3 dB, 2.4 dB. Okay, actually, when I match a top tone, it was supposed to be 0.5 dB. But because I use a resistor at the input, the total noise figure has gone up to 2.4 dB. Okay. Now, what I do is I change this part. Now look into this schematic. There is no resistor. Can you see this now? Okay. There is no resistor at the input side now anywhere. No resistor at the input side. You see that? Now the resistor is gone. Where is it? It has gone at the output. Okay. Okay. It has gone to the output side. Correct? I have done the matching once again. Okay. Why so many elements are there, I'll tell you for when we reach the layout point side. So I run it once again. Now you see here, how much is my noise figure? 0.7. How much is my, everything is same. 17.8 dB. Earlier it was 2.2. Okay. Now it is, and this is my stability factor. Instead of K, here mu and mu dash are used. I mean, it's again same K only. I mean, everyone knows about those things. As long as mu is greater than 1, it's similar to K only. So you can look into this thing also about the stability. Because of resistor, there is a stability now, and it is clear. There is no problem in the stability part also. Okay, what to do is clear. Okay, so now LNA is good. Everything is fine. I have good gain matching. See at the return loss now at the end. It is not good because I haven't matched it for a good return loss. I have matched it for a good noise figure. Okay, so output return loss is good, but input return loss is not good. That's where I was saying only solution is either you use an oscillator at the input, which will give you good return loss, or a balanced structure. That's the only way. Now, maybe if you run optimizer, you give up some noise figure, you may get a good match at the end. I have not done that. Okay. Come again. that system, I will consider that part. It will increase the minimal. Usually the isolators at 1.5, if you see, they will have insertion loss of only 0.24. I still have not. I mean, enough insertion. I will consider that factor in system part of it. I mean, after this, I will tell you what happens when you use a lossy element before that. But if you go for balanced configuration, there will be no effect.
You use the
balance means two elements. Have a divider.
if you use the emitter feedback, you can still get compromised.
I'll come to your feedback also. In power amplifier. See, this is very here. You know, instability in LNG, everybody has seen it, they can handle it. But instability in PAs, probably people are not aware because they are used to handling the PAs which are stable. Their only worry is about power. But the GAN is not like that as well. There is an additional problem with that. That is the stability problem. Okay, I'll come to that also. Next example when I'll take 35. Okay. Just 1 second give me. I would like to show something. I cannot run everything now. This is the layout. Same thing when you want to give out. Now I have done the design. I have done the simulation. I didn't use. I showed you like Smith chart. You can do the matching part. I think that's very easy. I have not used very lot of elements and all, but I have taken good enough bandwidth and all. Just one more point I would like to tell you. Broadband design, narrowband design. If you have that confusion, shall I do that part?
Yeah.
Okay. Okay. When you do this matching on a Smith chart, okay, do you know you can control the bandwidth? Again, on Smith chart itself, you can control the bandwidth during matching. Okay, right. So how do you do that? Let's say in this case, probably the problem was from 50 ohm. I had to go. I think if I would outside. The termination of tau s was on the right half of the Smith chart matching point, and probably it was around 100 if I am correct, 100 real power. Okay, correct. So I have to design a matching network from 50 ohm, because there is a source here 50 ohm, to 100 ohm. That was the thing. Okay. So I was supposed to design 50 ohm to 100 ohm. I'm actually doing it. Okay. Now, if you look at Smith chart, this is the normal Smith chart comes. Okay. This is how it comes. You activate the Q plots also there, along with this Q curves. You start getting this on top of that. This is in all the simulators you must have seen. Okay. You can keep the Q curves in drop mode, or you can bring the Q curves superimposed on the Smith chart. Starting with Q1. Okay. This is one part of it. Now, once I have to go from 50 to 100. This is the relation you use. Okay. RP is the parallel resistance which is always higher. This